From the vastness of outer space, Earth appears as a small blue world floating in silence. But as we move closer, we realize that its outermost layer, the Earth's crust, holds the entire geological story of our planet. It carries the memory of mountain building, volcanic eruptions, the formation of continents, oceans, and all the conditions that make life possible. Today, we dive deep into the structure and material composition of Earth's crust, the solid shell that has shaped our world for billions of years. The Earth's crust is the thin, rigid layer lying above the Mohorovičić discontinuity, the boundary separating it from the molten mantle below. Although it makes up less than 1% of the planet's volume, the crust is where every ocean, continent, forest, mountain range, and human civilization exists. This layer is constantly shaped by geological forces, and to understand Earth, we must first understand this outer shell. Scientists classify the crust into two main types: the continental crust and the oceanic crust. The continental crust is the thicker and older layer, while the oceanic crust is thinner and younger. There are also transitional forms such as subcontinental and suboceanic crust, created in regions where tectonic plates stretch, collide, or sink beneath one another. Continental crust, thickness and characteristics. The continental crust varies dramatically in thickness. In stable ancient regions called cratons, it is about 35 to 40 kilometers thick. In young mountain belts formed by intense tectonic compression, it reaches 55 to 70 kilometers. And beneath the highest mountain ranges on Earth, such as the Himalayas and the Andes, the crust can reach an incredible 70 to 75 kilometers. This remarkable variation reflects the powerful geological forces that shape our continents. Continental crust, classic three-layer model. Traditionally, the continental crust is described as having three main layers. The first is the sedimentary layer, made of sandstone, shale, limestone, and other sediments deposited over millions of years, ranging from 0 to 10 kilometers in thickness. Beneath it lies a thick sequence of igneous and metamorphic rocks. The upper part of this sequence is dominated by granite and gneiss, light-colored rocks with wave velocities between 5.5 and 6 kilometers per second, and it is typically between 10 and 25 kilometers thick. Deeper still is the basaltic and granulite layer, denser and darker, with wave velocities between 6.6 and 7.2 kilometers per second. This layer can reach 15 to 35 kilometers thick. The boundary between these two rock groups is known as the Conrad discontinuity. Continental crust. Modern model, Kola borehole. Modern research, including data from the Kola superdeep borehole, gives us new insight into the continental crust. According to updated models, the crust is divided into an upper, middle, and lower layer. The upper crust contains complex metamorphic rocks and ancient igneous formations. The middle crust includes partially ductile layers capable of slow horizontal flow, which plays an important role in tectonic movement. The lower crust consists mostly of dense granulites and mafic rocks, marking the transition toward the mantle. Oceanic crust. Structure and layers. The oceanic crust is much thinner, only 5 to 12 kilometers thick, averaging 6 to 7. It consists of 4 layers: ocean water at the top, a thin layer of marine sediments, a layer of basaltic lava formed along mid-ocean ridges, and a thick base of gabbro and ultra-basic rocks. Oceanic crust lacks granite, making it richer in magnesium and iron, and therefore denser and darker. Transitional crust. Subcontinental and suboceanic. Transitional crusts lie at the margins of continents. Subcontinental crust is found around island arcs and is 20 to 30 kilometers thick. Suboceanic crust forms where continental landmass stretches into the ocean. And in these regions, the sediment thickness can reach 15 to 20 kilometers. Material composition. Elements in the crust. To fully understand the crust, we must explore its chemistry. Elements within the crust are scattered, combined, and constantly transformed by geological processes. In 1889, Clark introduced the Clark value, representing the average abundance of each chemical element in the crust. These values act as natural background levels for evaluating mineral concentrations. 8 elements make up more than 98% of the crust: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. Oxygen and silicon alone account for 75%, forming silicate minerals, the fundamental building blocks of most rocks. Aluminum contributes about 7 to 8%, iron about 4 to 6%, and calcium, sodium, potassium, and magnesium each account for 2 to 5%. All other elements, including copper, lead, zinc, gold, and many more, make up less than 0.5%, which is why ore deposits are economically valuable only when geological processes concentrate these elements far above Clark levels. Material composition. Oxides of the crust. The crust can also be described using oxides. Continental crust is rich in silica, exceeding 60% SiO2 and producing lighter, more acidic rocks like granite. Oceanic crust contains less silica and more magnesium and calcium oxides, forming basalt and gabbro. These chemical differences explain why continental and oceanic plates behave differently during tectonic processes. Minerals are natural chemical elements or chemical compounds that form through certain physical and chemical processes in the Earth's crust or on the surface. There are about 2,500 minerals, of which nearly 50 are common and participate in the process of rock formation. The majority of minerals are solid, with only a few existing in liquid form, such as mercury, petroleum, and water, and some in gas form, like carbon dioxide, methane, and hydrogen. Common minerals found in the Earth's crust include quartz, plagioclase, mica, pyroxene, and olivine. These minerals not only influence the physical and mechanical properties of rocks, but also serve as the source of many important mineral resources. Understanding the structure and composition of Earth's crust helps us locate natural resources, understand the formation of ore deposits, predict volcanic and seismic hazards, and reconstruct the geological history of our planet. Every mineral, every element, and every rock records a chapter of Earth's evolution. Conclusion. Although the crust is thin, it holds the clues to Earth's long and dynamic past. By uncovering its structure and materials, we explore the hidden foundation of the world beneath our feet. Continue this journey as we venture deeper into Earth's mantle, core, and the powerful forces that shape our planet.